We shall continue with tuple relational calculus. Tuple relational calculus is a formal non-procedural query language which generates relations based on some logical expressions. The logical expressions are of the form TPT, which gives you the relational set, and we have seen how to extract the attributes of T and the tuples of T from this relation. This expression must be true for each and every tuple in T. Other than the standard connectives and or not implies, we have got two extra connectives which are called the there exists quantifier. There exists U element of the relation book and the quantifier for all U elements of the relation book. We have seen in details previously the use of the there exists relationship. Now we will see the use of the for all relationship. Let us take two examples. The first example is T for all U element of book, T title is equal to U title. Now what does this mean? For every tuple in T, this relation must hold. For each and every tuple in T, this relation must hold. Firstly, T has got only one attribute, title. So T will be a relation corresponding to a set of titles of books. Now take any relation, any tuple in T. So let it be a title compiler. This means that for this one, in book relation, which has got three attributes, title, year of publication and accession number, for this one, each and every relation in each and every tuple in book must satisfy T title equal to U title. This is the meaning of this expression. So what does this query reveal? This query will give you a title provided in this one there is only a set of books which is only compiler. And this query can return only one name. It cannot return more than one names, because if it returns more than one names, there must be more than one names here, which will violate this relationship anyway. So this query means that T for all U element of book, there can be only one book. So this returns the name of the book provided there is only one book in the library, not one book, at least one title in the library. There may be 5 books with the same title with different years of publication and accession numbers, but the title must be only one. That is the meaning of this. The for all query is not effective actually this way. This is not a common query. A common query is whenever for all is used, the implies relation usually comes into the picture. What does this say? This says T, and I am interested only in title. For all U element of book, if T title is equal to U title, then year of publication of U must be 1991. That is, now you can have many titles in the desired resultant relationship. Now suppose compiler is there. Here if a book is there design, which has got title design, it trivially satisfies the implies relation. The implies relation A implies B is satisfied is equivalent to not A or B. That is, if A is not true, this relationship is satisfied, but if A is true, then B must be true. Therefore, this compiler will trivially satisfy a book which has got title design. But if there is another book compiler, then the year of publication must be 1991. That is, you will find out that set of books such that they are only published in 1991. That is, if a particular book is published in 1991 and there are 10 copies of the book published in 1991, it will be there in this relation. If there is a book which is not published in 1991, it will not be there in this relation. And if there is a book which is published with the same title in 1991 and in 1995, then this also will not be there in this relation. It also means that if there is a book which does not have any title here, that title should also be here, because it may not match. A title may not be here, okay, and still it will. See, if I read abracadabra, there will be no book called abracadabra here. So should that be here, present in this relationship? For the time being, let us say no, because we are interested to find out tuples in books. We will come to this question a little later. So we are only interested in the relation book, and if compiler design matches, then it must be 1991. That is, we are going to find out those books which are published in 1991 and in 1991 only. That is the meaning of this relation. We will use that idea to solve this particular problem using the contains relation. T, for all S element of user, find the names and suppliers who have supplied titles corresponding to all books issued by Vijay. This is not all accession numbers, all titles. For all T, for T, that means for all persons such that Vijay has issued this book. This must imply that the title of this book has been supplied by this supplier, the supplier whose name will be given here. The supplier whose name will be given here, it must be that name such that for each and every element of Vijay, the book issued by Vijay must be supplied by this supplier. So if it is not Vijay, I am not bothered. But if it is Vijay, then there must exist P element of borrow such that P of card number must be Vijay's card number, and there must exist Q element of book such that Q accession number must be same as that in borrow, and there must exist another element in book which has got the same title. And there must exist a M element of supplier relationship such that the accession number of this new book, which has got the same title as the book issued by Vijay, must be equal to M accession number, and finally T of supplier name must be equal to M of supplier, and all the brackets and whatever. I want, in this tuple I will have only supplier name, and for this supplier name what must be true? I must see that for every S element of user, if it is not Vijay, I am least bothered. But if it is Vijay, then the card number of Vijay must match in the borrow relation. That is, Vijay must have issued some book. If Vijay has issued no book, it's trivially true. If Vijay has issued no book, I am not bothered. I don't want any answer to this relation. But if Vijay has issued a book, then the accession number of the book will be obtained by this, and I want the title of the book, and for this title the supplier which I want must have supplied this title. So I will get this title, and I will get the alternative accession number of the book with the same title. These two may match to be the same thing. It may be the same accession number, it will still match because there exists Q and R may be the same thing. So for this R, the accession number must be same as the book supplied by this supplier, and the supplier name must be this. So this is how I am sorry, this is B name. This is B name, this is not S name. This is B name. And this is S name. So this is how we get the contains or the divides by relationship. So a formal definition of tuple relational calculus will not be given at the present, but using these examples we can see that the connectives and, or, not, and the use of the two quantifiers for all and there exists, if done properly, can be used to form any such expression. The formal syntax of relational algebra and relational tuple relational calculus I will not provide now. It will be required in a later phase, when it is required we shall see it. Domain relational calculus is also similar to tuple relational calculus. It has got a syntactic difference in which you have to specify the attributes slightly differently and more specifically. Rather than in tuple relational calculus, the attributes have to be extracted. In domain relational calculus, the attributes have to be specifically written. The syntax is slightly different, but the notion and the nature are more or less identical. Before terminating, we shall see what are known as safe expressions. Now we can write out queries which have got arbitrary answers. Now attributes come from sets. The domains of attributes are defined as integers, reals, and all that. Now suppose we write down this query: T, find all T such that T is not an element of book. What does this mean? This will have the same attributes as book, that is year of publication, which is an integer, a 4-digit integer, title, which is a set of characters, and accession number, which is another set of characters. The question is, find all T such that T not element of book. That is, find out those books which are not there in the library. Now the question is, how will you get this? What is the answer to this? And if you look at the definitions of the domains, you have not defined the whole set of books available in this world. And from the domains, you will just find out those possible tuples which can be formed as proper domains, that is those strings with year of publication, names and accession numbers which can be formed and which do not match with these tuples. So you will get a huge set of infinite arbitrary, not infinite because of the finite size, but you will get a set of arbitrary relations, and this is meaningless. And in some cases, when you define integers, then this set may become infinite. Therefore, such expressions are called unsafe expressions, and they are not really relevant to our domain of discourse unless you have a universe of all the books known to you. So for that, we define what is the concept of DOM P. The DOM P is defined as the set of all values referenced by P. P is a predicate. Now this predicate, let us see the examples of DOM P. If I write down any predicate PT, so I may write down this as T element of book. So domain of P is the set of books. I may write down there exists U element of book. Here again DOM P is book. I may write down a query there exists U element of book such that U of title equal to something, and there exists S element of supplier. Then the domain of this whole expression is the domain of book and the domain of supplier. That is, all the relations which are used in this particular expression, the union of their attributes, and let us say the Cartesian product of that is my domain. That is, in the predicate P, I will use a set of relations, and I may use the relation 5 times. The Cartesian product of all the relations which I use is called the domain of P. If I use it 2 times, then twice. That gives me my domain of that particular relation. The expression TPT now is said to be safe if all values that appear in the result are values from domain of P. Okay. This is not safe because the results which appear here are not from book. If you really want to have the relevant things, then you will not get those which are from book. So you have to define the set of universal books and say that T such that T is an element of all books, some all books relation must be there, and T is not there in the book relation which is there in the library. Then you will get something which is safe, because now you will have the 2 possible domains, books and all books, and the tuples that you will get will be part of the all books or books combination. So in that case it will be safe. So an expression is said to be safe if all values that appear in the result are values from DOM P. In this particular case, if we start including those books, if the name is not Vijay, then anything can be there, then all names can be there, even those who are not users of the library. But if we restrict it to safe expressions, then we will get only corresponding to Vijay. So we may say that tuple relational calculus may be restricted to safe expressions, may not be restricted to safe expressions. Okay, there are 2 types of categories which we can provide here, and there is an interesting theorem which relates tuple relational calculus expressions with relational algebra. Tuple relational calculus restricted to safe expressions is equivalent to relational algebra in expressive power. This means that any safe tuple relational calculus expression can be written in relational algebra. It also means that any relational algebra expression can be written as a safe tuple calculus relational expression. This is true even for domain relational calculus. There again safe expressions are equivalent to relational algebra in expressive power. We will not do the proof of this, but the proof of this, the outline of the proof of this is like this. We will see that in relational algebra there are a set of 6 fundamental operations, and all relations are formed by combinations of these fundamental operations. If we show that corresponding to each fundamental operation, if R1 is a relation formed out by some relational algebra, R2 is another expression formed out of relational algebra, and we combine them by the fundamental operations, then and for each of these fundamental operations we produce a tuple relational calculus expression, then we will show that for every relational algebra, and if the tuple relational calculus expression is safe, then for every expression in relational algebra we have an inductive proof that there is a safe tuple calculus relational expression. And once we know the exact formal syntax of tuple relational calculus, then there we will see that there also The tuple relational calculus expressions are formed by a combination of two expressions having connected by either or not, or and, or implies, and some of them may contain there exists quantifier or for all quantifier. And these 5 cases, for each of these 5 cases, we can see that we can write down the equivalent relational algebra expressions. If it is safe, the equivalent relational algebra expression can be written down. So that way we have to give 2 directions, and based on these 2 directions of the proof, we will get an answer to this theorem. I will not do it, I will leave it as a simple exercise. It can be also found in any standard textbook.